Alright, so we're DryArmor Systems. My name is Tim Marco.
I'm Caleb Miller.
We have two other members of our group. Obviously, you can see they're not here. They're from the football team. They're down in Virginia playing in a bowl game. So we're hoping that they get big wins and they miss our presentation. But that's alright. We still have some audio recordings of them on some of our slides so you can hear their voices. So to introduce myself and Caleb, we are part of the men's lacrosse team here at Wilkes University. Obviously, Brandon and Anthony are also they're part of the football team here. So this project is something that we kind of deal with our everyday lives. We go into practices with them being during the summer. They have really hot practices, play in rain. You know, we come back and our pads are still wet from the night before, the day before. So we were looking for a solution to be able to dry our pads overnight and make sure that when we come back the next day, that we're being able to put on dry pads and not having to wear wet, soggy pads for practice that day. When we looked into what was already on the market, you can see there's a hoop drying rack and there's this kind of this pad drying rack. That wasn't very effective and it wasn't very utilized in locker rooms. So our system would be put into the locker room to kind of solve this problem.
Our solution to drying athletic equipment and football pads took inspiration from the NFL helmet heater systems that they use on their sidelines. Their systems are used to keep helmets warm in the winter because when it's cold out, the pads get hard and it's uncomfortable and it's unsafe for the players. Their systems are built using PVC pipe, and that's what we got our idea from. An early sketch that I made is on the left here. You can see it has a section for gloves and a helmet and our shoulder pads. This is designed to where it can go from one locker and then it can be modular up to 3 lockers.
In order to narrow down the requirements for this design, we contacted our head football coach and talked to him about possibly putting this design into the football locker room. Therefore, our system is designed to be put in the football locker room and based around that. We want each locker approximately to receive the same amount of air. Our shoulder pads, gloves, cleats, and helmet will all be able to be put onto our system, and we want a different distribution of air to go to each pad. So our shoulder pads will receive the most amount of air. Our gloves and our cleats we want to receive the second most amount of air, and then we want the helmet to receive the least. Also, we want both ends of the glove and the cleats to receive relatively the same amount of air.
So specifications for this, for right now, we designed it for 1 locker, but we're hoping that it's going to be modular, so we have 3 systems, but for this project itself, it's only 1 locker. We're using Schedule 40 PVC pipe it's a cheaper option of PVC, and the actual heat that can withstand it is acceptable for this. Each locker is approximately 93 CFM of air, which is 280 for all 3 of them. We're looking for a max temperature of only 105 degrees. This is the standard for all industrial boot dryers, and it was also underneath that 130 maximum for the PVC itself. And everything will be running off of 120 AC as it is meant for commercial usage. We can just plug it into an outlet.
This is essentially our work breakdown structure. We decided to break it up into 3 components: mechanical, electrical, and then all the way up we have our management portion. We're kind of for the mechanical side of it. We wanted to first come up with our design, and then we wanted to go through the airflow, get calculations, get results, see how the airflow would go throughout our entire system. Then we had to find our heater and blower, which we were originally going to build, but we decided to end up buying one, which you'll see later in the presentation. And then we just need to get to our testing portion of it. And then for electrical, we need to go through our heat sensing, which we will have a temperature sensor to make sure that we don't go over that 105-degree temperature with our Arduino board. And then how hot it is, how fast the air is going through. And then finally, do some control testing. And on the management side of it, get our requirements in, get our specifications down, finalize our budget, and just come up with our schedule moving forward.
So this is just a little overall schedule. Our basic things were kind of built off of the schedule for senior projects 1 and 2, where presentations. So, for instance, prototype 2, that due date for us is the first day of presentations of the prototype, and then the final spring presentation is the date of the spring presentation, and we kind of gave ourselves 2 weeks for the actual building of the model, and then 2 weeks for redesign.
Here we have our current design of our system. On the left, we have the complete assembly on SolidWorks. The blower is on the ground or possibly on the cart would be for if the user wants to supply multiple systems with one blower and fan. Then we go to the top portion, which just sits on top of the locker. This is where the actual drying of the equipment will be. The two horizontal tees are for the cleats and gloves, while the vertical posts
They provide up to 300 CFM. It runs off of 120 AC, and the heater is 4,500 BTUs. In order to get this into our 4-inch round PVC pipe, we're going to use an adapter. This is common in HVAC systems. It goes from 4-inch round to a 10-inch by 4-inch rectangle. We could easily modify this to get to exactly fit the heating element attached to the blower. And then we're going to use an aluminum duct. It's flexible, it can attach to this adapter and then bend 90 degrees attached to the vertical PVC pipe on our system. This is the outlet valve design that we're going to be using on the glove and cleat portion of our drying system. As you can see on the right, when the valve is open, the holes are going to be lined up. And then when you can rotate the cap to close the valve. This is going to work similar to your ordinary salt and pepper shaker. The reason we have this is that if a player doesn't use gloves, you can close the valve to prevent the loss of heat and air out of the system, giving more heat and air to the parts that need it. This is the budget for our project. The table on the right shows the cost for one locker. All the PVC pipe is from the same bulk retailer, which saved us quite a lot of money. Our blower heater combo costs $150, which is more money than our original option, but we determined it was a safer bet to ensure that our project works. We got the adapter to go from the blower heater combo into the flexible duct off of Amazon. Flexible ducts is coming from Home Depot, and all of our electronic components are coming from Amazon. We are coming $83 short of our $500 budget with one locker. Ideally, we would like to use the system for 3 lockers, but we would have to get budget approval to do 3 lockers. The total for that would be $512.
We did a flow simulation on SolidWorks in order to get the correct configuration of our outlet holes and the sizing, just to make sure that we get the correct airflow that we were looking for before we prototype any parts. In order to do this, we had to create a simplified system for the simulation. So our assembly was not working in the fluid flow simulation. So I had to make a singular part that's simplified so that everything was airtight and then we could actually run the flow simulations. Some boundary conditions that we had to set for this simulation was the inlet is 4.667 cubic feet per second, which is equivalent to our 280 CFM that we have from our blower. And then each outlet hole is configured to an environmental pressure outlet. What this basically means is that each outlet is the air is getting released to the atmosphere. And then each outlet is giving us a volumetric flow rate for our results. which what that will be able to do is we'll be able to see how much each piece of equipment, so how much CFM each piece of equipment is getting, and then we can match those results, tweak the design to get a desired airflow from our requirements. These are the different configurations we ran our fluid flow simulation with. The first configuration was more of a test simulation to ensure that we were getting results from the simulation. For all of the configurations, the first T is for the gloves, and then the vertical post is for their helmet, and then the second T that's the furthest away from the vertical pipe is where our cleats will go. The second configuration here has the holes horizontally on the face of the PVC cap, that's for gloves, and then our post for our helmet now has a revolved holes around the top, and then our cleat T has holes facing downwards so that the air goes into our cleat, and now our shoulder pad dryer on the 4-inch PVC pipe has much smaller holes. And then for our third configuration, the only really change is on our glove drying portion. I took out one hole because we were getting a little too much air through the gloves. Here are the simulation results for our first configuration, along with a visual of the flow simulation on the right. We separated this test by cleat and glove flow, the first and second shoulder hole, and then the helmet hole as well. As stated earlier, this is more of a test simulation just to ensure that we're getting correct results. As you can see, we're getting average values for our cubic feet per second. Our helmet is getting way too much air. We stated that we wanted that to get the least amount of air, and that is currently getting close to the most. And then also our cleats and gloves are not getting nearly enough. Here are the results for configuration 2 and 3. First, we'll start with configuration 2. We actually get the correct distribution of each equipment here. The shoulder pads are getting the most air, and then cleats and gloves are getting the second most amount of air, and our helmet is getting the least. There's a slight difference between how much air the gloves are getting and how much air the cleats are getting. So as you can see, we have 15% of the total air going to each glove, and then 13% going to each cleat. Ideally, we would like to get those closer, but they're not bad. And then we have our helmet getting the least amount of air, and then our shoulder pads with 17%, close to 18% on each side, getting the most amount of air. Configuration 3, where I decreased the gloves holes by 1, got actually much worse results. So the gloves now are only getting 10% of the total amount of air, while cleats are getting close to 16, and then the shoulder pads jump up to 22% and 18%. Our helmets still stays low at 8%. There actually is we still have the correct amount of distribution to each equipment. However, the distance between how much air the cleats are getting and the gloves are getting are too great. So actually, our configuration 2 has the best results.
So here just kind of a closer up of our two configurations from the second one and our third one to see how the airflow works out. We talked about on the last slide. This is just an image for you guys to see.
So here's just a simple flow design of what the electrical will be. So it's coming from power, which is the outlet in the actual locker room. It's going to the timer switch, which has per hour, and then it goes to the fan control and rectifier to the Arduino, and then before it reaches the thermostat to control the coil, it goes through a relay, so that way when it's over 105, power's cut off to that.
Some ethical things, we're just worried about public safety, that's our main concern. That's why we have a thermometer in there. We just have to be responsible about reporting what's going on if the PVC is getting too hot. If anything's overheating, we just have to be very transparent about how we're going about our project and moving forward with the risks of it.
Our testing plan is just, next semester, is just to make sure that, that at that 105 temperature, it is shutting off, and once it reaches a certain temperature below that 105, the heating coil won't be able to kick back on through the code of Arduino.
And then moving forward, we just gotta finish up our testing, essentially build it, do some safety checks, make sure all our wiring is working correctly, making sure that if it does overheat, that the whole system can shut off, and just making sure that we're not overusing energy. Just some final, once we have it built and our prototype is ready, some final little things here and there to make sure that everything's gonna go according to plan. And then kind of in conclusion, we just wanted to create something that would solve a real world problem that we face every day. It's not applicable to everyone, but to athletes it is. Like football, men's lacrosse, ice hockey even, they kind of deal with this stuff a lot. So we just want to make sure that our project will be able to solve that. And then kind of once we get into the testing process, make any final tweaks here and there to make sure everything's running smoothly, everything's running correctly, and hopefully be able to put it into the football locker room view. Here's our reference for our ethics stuff. We'd like to thank Coach Boers. He's kind of been supporting us through this whole thing. We've talked to him about if this does work out well, we can prove that it works, that maybe it be put in the football locker room over the summer. Not for sure yet, but that's something to keep in the back of our minds moving forward. Any questions?
So you did go over time, but I know you were kind of working with the technology, so just keep that in mind for next semester going forward. You probably could have sped up the test results section.
Yeah.
So. Okay, any technical questions for the
Okay. So, for the part of your team who could not be here today, is the assumption that they're going to be the ones testing your prototype next semester?
We'll both be testing it. I mean, it might be easier for us to use our pads because we'll be in season, we'll actively be using them. So especially after games where like we play in the rain and we have practice where it's pouring down rain and our stuff is soaked, it'll probably be the best time to test it to see how well it actually works. I mean, we've been pretty balanced with it. They've been in season this semester, we'll be in season next semester, so we've just had a pretty open line of communication on who does what and what's going on. So.
My first question is like, how long is it going to take to write that system that you want to put in there? And the second question is like, in terms of energy, how much energy are you expecting that you are going to use to run the system?
So with the system itself, it depends on how wet the pads are. We're going off of kind of like the timer. It's in hour sections, so it's going up to 8 hours. A lot of these boot dryers, we kind of took reference off of them. Their kind of max is 8 hours. So we believe that at 8 hours, it should be sufficiently dry. And then with the actual energy coming off of it, it depends on how long we are running for it. I mean, we have the wall, it's around, I think the output power right now is around 1,800 watts. So again, it's going to depend on how long it's going to be on, because the system is either going to be completely on or completely off just because of that timer switch.
I think that for the next semester it would be great to run your system for the worst scenario, so you can provide the numbers for those calculations. And one suggestion is going to be the balancing of the air. So the air is very smart, and you are going to find preferential flow. So when you are doing the simulation, you are assuming that all of the air are going to reach those specific spots. But when you are like testing, you are going to find challenge with that. So it's something that is going to be very important to address.
So, do you guys have any sensors in your system?
Yeah, it's in the actual model itself. We're putting the. We'll go back to the actual thing now. We're going to put the temperature sensor right outside of that blower, towards that PVC connection right there. We want to kind of keep it on the actual module area itself, so that way you can eventually take it apart, like take it off that PVC and move it to another system.
Okay. So you have one temperature sensor?
Yes.
Okay. So another thing is that, like, you see, if you turn off your valve, you're supposed to turn off the heater, right?
Yes.
And the blower as well, right?
Yeah.
But that's a commercial system. Anytime if you want to tap into a commercial system, how would you tap into that commercial system? I mean, that commercial system is like plugging in this button and on. How are you going to break it? Are you going to try to like disassemble it and try to, plug your core system into it? How would you do that?
So the way our system would work is, say you take the blower dryer, you plug it up into that PVC. When you plug it in, you have to turn that timer switch on. So the timer switch kind of takes the power from the receptacle to the actual fan control itself.
Dr. Zhu's question is how are you going to control the heater and the lower second?
Oh, okay. So with the actual temperature sensor, it only knocks off the heater. So there is a separate control for a fan, which is a 2-speed fan, and a separate one, which is a thermostat for our coil itself.
So are the heater and the blower running with that or two separate?
Do they have to run at the same time, or they cannot? I guess that for commercial system, they have to be running at the exact same time. Right?
Yes.
Anytime the line is on the other one, then that's exactly a problem for you.
The heater is separate.
Yes. Okay.
So yeah, the heater is separate. So
But is it one piece of commercial system? It's two systems.
Yeah, two different
I
systems.
see. Okay, so that I didn't understand that. Okay. But when you tap into a commercial, I mean, if you're talking about go there, break open something of a commercial system, that's something you should be really careful about because you might for me it's too much of a risk. Okay. But for you, I think the easiest way for you to just use a relay system to cut off the power. That might be the easiest way to do it. Other than that, anything else, I feel like the risk is a bit too high. You want to keep your existing system, commercial output system like intact as much as possible. You see what I mean? You don't want to like open it and try to tap into it because you risk really breaking. Okay, just like do a separate step along like almost like circuit breaker kind of thing and use that to control your system.
Okay.
Okay. Thank you, team.